Hey everyone, welcome to our next video. I hope your day is going well. Um, Hopefully this one won't be too long. I'm recording it right before one of my other classes. So this one is going to be 4.1, which is inverse functions. So first, when we talk about an inverse function, really what we're saying is inverse is very, like, basically we switch the x's and the y's and it'll make a new function. And we'll see some other properties that kind of happen with the inverse functions. But a big reason that we're talking about them right now is that we're about to move into exponentials and logarithms. And exponentials and logarithms are inverse functions of each other. So first we talk about inverses and then we kind of move over there. So first, a function must be one-to-one to be invertible, meaning like to have an inverse. Let me write it that way. To have inverse. Now to find out if a function is one-to-one, it means that there's one x value or just input value to one y value or output value. So if you remember with just functions in general, a function, you just couldn't have repeating x values. But you could have like repeating y values and that was fine. For instance, like a parabola, you're going to have repeating y values, but you can't have repeating x's whenever you like write the points out. With a one-to-one function, you need both to only be like one x to one y and that's it. So for instance, a parabola is not a one-to-one function. We can also see one-to-one by doing the horizontal line test. So for instance, if we think about a parabola, that is not one-to-one. If we hold up a horizontal line to it, see how we touch more than one point at a time? That means it fails the horizontal line test. So this is not one-to-one, which means we cannot take the inverse. Now for those of you who are going to maybe go on to the 240 series, there is still a way that you can take the inverse of a function like this, but you have to do what's called restrict the domain. Basically, we could say, okay, what if we only look at half the parabola? And then we'd be able to find the inverse. So that's for later, though. We won't do anything like that necessarily right now. Another way we can determine if something is one-to-one is with some algebra. So a function is one-to-one if and only if f of a equals f of b implies a equals b. What I want you to remember is that these are, I didn't mean to do, okay, there we go. These are y values. So what we are saying is if we can set two different y values together, set them equal to each other, do we get that actually those were the same x values to begin with? So basically, if we plug in two different x values into the function, do we get that they are actually just the same x value? I hope that makes sense. I'm going to say it again. If we plug in two different x values, so we're plugging in two different x values, do we get that they're actually the same x value? And I'll show you what this looks like, of course. So example 1, I'll determine if the following are 1-to-1. So part A, we're going to start off with y equals 2x plus 1. And so remember, y is the same as like f of x. So what I'm saying here is I'm going to start off with f of a equals f of b. So I start off here. I have f of a equals f of b. Then we're going to plug a and b into the function. So I get 2a plus 1 equals 2b plus 1. Then I simplify. So if I subtract 1 from both sides, I get 2a equals 2b. Then I can divide both sides by 2, and I get a equals b. Since I started with f of a equals f of b, and I was able to use algebra to get to a equals b, that means I'm done, and yes, this is a one-to-one function. This little box here at the end just means like I'm done with what I was doing. Kind of a math notation thing. Let's do another one, and this one is not going to be one-to-one. And so again, what I'm going to do is I'm going to start with f of a equals f of b, which just means plugging in a and b. Now the issue is when we do the absolute value functions, remember that they have multiple options. You can have a equals b, or you can have a equals negative b. That's coming back all the way from 1.6 is when we did absolute value functions. Since the signs are different here, we would say no, this is not one-to-one. Also, if we were to graph it, it does not pass the horizontal line test. So what's happening here is that what we're saying is two different x values, a and b, were able to give the same y value. So a and b for this one are actually not the same, because you can have a equals b or a equals negative b. So that means they don't have to be the same value, but they actually gave the same y value. So that's not working. That's not a one-to-one function. Next, we'll talk about actually finding the inverse. So your first step is usually going to be to check if it's one-to-one to see if you can even find the inverse. And then we'll talk about how to actually find the inverse. So let's do that now. So I have some steps for you. It's kind of called like a switch and solve method. Our first step is we're going to replace f of x with y. And I mean, if it already says y, then that's great. But if it doesn't, then we'll go ahead and replace it. Next, we're going to switch x and y. Next, we're going to solve for y. Next is really just notation. It says that we're going to replace y with f to the negative 1 of x. That's the notation for the inverse function. And then we're going to check that our domain and range switched. That's something you'll notice. And it's because you swap the x and y. So remember, since x is domain and range is y, and then if you swap those x's and y's, you'll see your domain and your range switch. But that last step is just really more of a check. Again, I just want to reiterate, this is just the notation for inverse. It's not the same as seeing like 1 over f of x either, so don't get confused there. It's a different type of idea. All right, so for example 2, we're going to go ahead and find the inverse. So I'm going to say find the inverse function. And yeah, we'll just leave it there. So I have f of x equals 4x minus 1. So the first thing that I do is I switch it over to y. Then I switch my x and my y. So I'll have x equals 4y minus 1. So I switched x and y. Then I need to resolve for y. So I'll move this 1 over, so I have x plus 1 equals 4y. Divide by 4, so I have y equals x plus 1 divided by 4. So that was it. All I had to do was solve for y. Now I go ahead and change that notation to look a little bit better. So this says the inverse function of f of x is x plus 1 over 4. Now for this one, for step 5, because we were just dealing with a line, like 4x minus 1 is just a line, so you'll see that the domain and range were both negative infinity to infinity. So not super great for checking, because this one, the domain was negative infinity to infinity. The range was negative infinity to infinity. On our new function, it also stays the same. But, I mean, they did swap, so. Now I also want to show you like what the inverse actually does. So I think it would help to see like graphically what is happening here. So I'm going to do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We can kind of see like why do we care about this? Here, this one's a little spaced out too much. Let me fix it. Yeah, that looks better. So I'm going to do the old one in pink. So I have a line. So I start at -1, and then I'm going to go up 4 over 1. So 1, 1, 2, 3, 4, and then over 1. So right here. And I like to get 3 points usually. I mean, 2 points is fine for a line, but 1, 2, 3, 4, and then over 1. So something like this is our old line. And now our new line is x plus 1 over 4. Now, that might be a little bit difficult to graph. So something I want to show you is when we swap those x's and y's, we can do that with the points as well for graphing. So the points that the original graph went through were 0, -1, 1, 3, and -1, -5. I just wrote down the points that I plotted. My inverse function, I just swap the x's and y's. So it's going to go through -1, 0, 3, 1, -5, -1. So I'm going to graph this. And so I really just want to show you like what the inverses are actually doing. They are reflecting over this line right here in the middle, which is the line y equals x. So that is the property of inverses. They reflect over the line y equals x. Kind of cool. Let's do another just like finding the inverse function. And I probably won't worry about graphing this one, but you could if you wanted to. Let's do f of x equals, let's do a little bit harder of one. I'm going to say x cubed plus 4, yeah. Yeah, we'll just leave it there. X cubed plus 4. So you should pause and you should do this one on your own. But step 1, we'll replace with y. Then we swap my x and my y. And now I just need to resolve for y. So I get x minus 4 equals y cubed. To solve for y, I can take the cubed root. So I get y equals cubed root x minus 4. And then I like to change my notation. Oh, sorry, I still wrote y. And there you go. There's my inverse. Some more that we can do with inverses is what if they're written as sets? So this one says find the inverse if possible. So part A, we'll do f equals, and this one's going to be a set of points, so negative 2, 3, 4, 5, 2, 3. And then part B, we'll say G is the set of points 3, 1, 5, 2, 7, 4, and 9, 8. So when we say like if it's possible, we want to check if it's one-to-one first. So if I look at our first one, the f function, you see how I have two of the same y values? This is not one-to-one. So it is not possible for us to get the inverse of that. Now this one, G, is one-to-one, meaning we have one x value to one y value. We don't have any repeats going on at all. For my inverse function, I would just swap the x's. And so I'm writing some notation here. This is the notation for the inverse. I'm just writing that -1 on top. And so all I have to do here is switch all my x's and y's, and that's it. Something kind of cool with the inverse functions that you can see is if you plug in something. So let's say if we do g of g inverse of 1, I should get back 1. So if I look at here, g inverse of 1, so I'm going to look at my g inverse function, and my x value is 1, so I would get back 3. And then if I go to my g function and I look at 3, oh, my y value I get back is 1. So see how we plugged in a 1 and we got back a 1? This is another property of inverse functions that we will see. And it basically means like if you plug in something to the inverse function and then you plug that answer into the original function, you'll get back what you put in. I know that sounds a little weird. So here's that property kind of written out. It says two functions, f of x and g of x, are inverses if and only if, and if and only if is actually really strong in math, f of g of x is equal to x, and g of f of x is also equal to x. So this actually brings us back a little bit to 2.8 of doing composition of functions. But it pretty much says if you plug an inverse into the original, you'll get back your x value. And that's what we just showed right here, right? We plugged in 1, so we got back out 1. This one is just writing it with x's. So of course we'll do an example. So example 4, we'll say check if the following functions are inverses. And we'll say f of x equals x cubed minus 1 and g of x equals cubed root x plus 1. So we're going to see if these are inverses by plugging them into each other. So right now our goal of what we want to see is we're going to do f of g of x, and we want to see that simplifies to x. We're also going to do g of f of x and see if that simplifies to x. If they do, then they are inverses. If they don't, like if one of them is even off by a little bit, then it wouldn't be inverses. All right, so we start off, we're going to do f g of x. So this means I'm plugging g of x into my f of x. So I'm plugging in the cubed root of x plus 1 into my f function. So everywhere I see an x, I'm going to replace with this parentheses. So I get cubed root x plus 1 cubed minus 1. Then I keep simplifying. These cubes are going to cancel, so I get x plus 1 minus 1. And then the 1's cancel, so I get back x. So this is good. Now let's do it the other way. Let's do g of f of x. So f of x was x cubed minus 1. So I'm plugging that into my g function. So my g function says cubed root x plus 1, but instead of x in those parentheses, I'm going to write in x cubed minus 1 because that's my f function. Then we can simplify. So I get cubed root of x cubed minus 1 plus 1. The 1's will cancel, so I get cubed root of x cubed, which cancels, so I get back x. So they are inverses. Because f of g of x equals x, and so does g of f of x. So if you plug them into each other, you get back x. Now for my last problem, I just want to do one more of like showing one-to-one and inverse. So show the following function is one-to-one and find the inverse function. And we're going to do f of x equals 2x plus 1 over 5x minus 3. So a bit harder of one than we've seen before. This one's hard because it has multiple x's in it. First, I'm going to show one-to-one. So I'll do that right here. Now to show that something is one-to-one, you start off with f of a equals f of b, and your goal is to plug in that a and b and then do a bunch of simplifying to where you just get a equals b. Usually if it's not one-to-one, the issues that you're going to see is like one is going to be positive and one is going to be negative. You're going to have some like pluses or minuses or something like that happening is usually what happens if it's not one-to-one. Kind of like with the absolute value. But as long as you get a equals b, you're good. So I'm going to plug in a, so that would be 2a plus 1 over 5a minus 3. And then on the other side, I'm going to plug in b, so I get 2b plus 1 over 5b minus 3. And now we need to simplify this. So in general, when we have fractions, we can multiply by our denominators. So I'm going to multiply both sides by 5b minus 3. Which will cancel it out here. And then I'll multiply both sides by 5a minus 3, which will cancel it out over there. Now we got to be careful here because we need some parentheses. So this is now 5b minus 3 times 2a plus 1 equal to 2b plus 1 times 5a minus 3. You may also know this as cross multiplying. Now I'm going to distribute. So if I distribute this, I get 10ab minus 6a plus 5b minus 3 equals 10ab plus 5a minus 6b minus 3. We can do some simplifying. These 3's will cancel. These 10ab's will cancel. So I have negative 6a plus 5b equals 5a minus 6b. I can move like terms to one side, so I'll do minus 5a on both sides, and I'll do minus 5b on both sides. This gives me negative 11a equals negative 11b. Divide by negative 11, and I'm left with a equals b. And so we're done. So yes, they are one-to-one. And we used our algebra to show that. Then over here, let me go ahead and do my inverse. So with your inverse, my first step was to switch that f of x to a y, just because looking at it as y makes it a little easier to work with. Then I'm going to swap my x's and y's. So because I have multiple x's, I'm now going to have multiple y's. Now I got to try to solve for y. This denominator is kind of annoying, so let's go ahead and multiply by it. So I'll be left with x times 5y minus 3 equals 2y plus 1. We'll actually distribute this x now because the issue is now we have a y trapped in parentheses. We don't want that, so we need to distribute it so that we can get it out. So I have 5xy minus 3x equals 2y plus 1. Now I'm solving for y, so I'm going to go ahead and move all my y's to one side and anything that isn't with a y onto the other. So this is going to give me 5xy minus 2y equals 3x plus 1. So I basically just swapped these two. Now, on the side with my y's, I can factor out a y since it's a greatest common factor on that side. So if I do that, I get y parentheses 5x minus 2 equals 3x plus 1. And my last step here, now this is great because we just brought it from having multiple y's to now we have one y. So I can divide by 5x minus 2. So I get y equals 3x plus 1 over 5x minus 2. And lastly, just notation, we would switch this into f inverse x equals 3x plus 1 over 5x minus 2. And there you go, that's my final answer. Now this is probably the hardest it can get. You won't see any that are harder than this. But a lot of algebra going on there. So this is actually it for this video. And if you have any questions, of course, reach out to me. I would love to talk to you. And I hope you all have a wonderful day. Bye-bye.